Okay. And from 3.4? Right, that's right. We did mechanical vibration, mechanical signals. All right. So number 4 in 3.4. So the body with mass 250 grams. Gotta be careful with the units here because I think in this one they mix up some stuff. Grams and meters. Grams to kilograms and centimeters to meters. So that, at least that's not so bad. And what part of a kilogram is this? Right. I had to look it up because I forgot. I was like, are there 1,000 grams in a kilogram? It would make sense, kilogram. But centimeters to meters, I was like, I have no... Yeah, cent in French is 100 centimeter. And I was like, yeah, it's got to be 100. I was like, 100 centimeters, that's so short. Meter, like, this is it 1,000? I had to look it up. Just brain dead for a moment. So 250 grams, end of the spring, that is stretched 25 centimeters by a force of 9 newtons. So that's the force, is 9 newtons when it is stretched 25 centimeters, right? 25 centimeters is what portion of a meter? Yeah, that's very nice. 25 centimeters, oh wait, 100 centimeters is a meter, right, okay, again. So we need to know what the spring constant is. And so they give us the actual raw, the force, 9 newtons, when it's stretched 25 centimeters from its equilibrium. What's the spring constant? How do we find that? Right. Because if this is positive, that means the force is acting the other way, which means it would be going to the left, right? Right, so we could say, so in other words, the force will be negative 9 newtons when x is 25 meters. The spring constant, let's see, where do we get that value? Because that will give us the value for k. So the spring constant, remember, f sub s, negative kx. So from that, we know that negative 9 newtons is equal to negative k times x. And that allows us to actually solve for the Hooke's constant in this problem. Why don't I keep walking over here and hold on to this? So solve this for k, and what do we get? Divide by negative 25, so the negatives cancel out. That's nice. Right?
25 or 0.25?
Oh, right. Newtons, and we're talking about meters, so it's 0.25. Right, we want it in Newton meters. 36. Right. So divide by 0.25, that's the same as multiplying by 4, we get k equals 36. So our equation would be x double prime, what is it normally? K over m. What's the order of these? K over m. C over mx plus k over mx equals 0. So that would be the situation there. And in number 4, they also say, what else is going on? There's no dash pot attached to it. So this is just a spring situation, right? All right, time t equals 0, the body is pulled 1 meter to the right, stretch the spring set in motion with an initial velocity of 5 meters per second to the left. Okay. So this is undamped. What does that mean?
It's not wet.
There's what? There's no what?
No seal. It's not wet.
Okay. It wasn't as fun as I thought it was going to be.
Oh, man.
So undamped, C was the damping constant. In other words, C equals 0, so it knocks out that term. We get the x double prime plus k over mx equals 0. And they said let omega naught equal root k over m. So that means that omega naught squared is the k over m. Yeah? Okay, so the characteristic equation, we worked that out in the general case last time, right? The characteristic equation had solutions. Where are they? Negative p plus or minus square root p squared minus omega naught squared, where p, 2p was equal to c over m. Is that right? This is undamped. So we don't need this equation because c is 0. Sorry, orienting myself. So this is undamped. We don't need this situation. This is when there is damping. We talked about the critical case, or overdamped or underdamped. So we can just solve this, right? X double prime plus omega naught x equals 0. So the characteristic equation will be what? Assuming the form e to the rx, x equals e to the rt. Yeah, sorry. Omega naught squared is that, yeah. Okay, so with x being e to the rt, we get characteristic equation r squared plus omega naught squared equals 0. So r equals plus or minus square root negative omega naught squared. Pull out the negative 1, and that's plus or minus I times omega naught. That's why we let omega naught squared be k over m. Then we get r equals, so this is the imaginary part of this number, omega naught. And we got a 0 here. So the solution for x involves the cosine and sine, right? C1 cosine, and it's the imaginary part becomes my coefficient, omega naught t, plus C2 sine omega naught t. Okay? Now it's coming back to me. Omega naught is k over m. Right. Now, on the homework list it said just solve and determine if it's damped, overdamped, critically damped, underdamped. In this case it's undamped, and I said we would disregard actually writing its form as a single sinusoidal function, right? So it can be done. You can look up in your trig books, and as long as you have the same the same period, these can be written as a single sinusoidal function. Okay, so I'm not so concerned with actually doing that. We can find the important things about this anyway. I'm not concerned with phase shift, right? That's like a lag time. Not concerned with that. What I'm concerned about is the period, the frequency, and the magnitude. Okay, but we can find that all from this form. So again, putting these in here, we got cosine. Well, let's just leave it omega naught, and we'll solve for that and deal with that when we're done. All right, so we do have initial conditions, right? They were at time 0, the spring was stretched 1 meter, was it? Wasn't it 1?
I said that. When I was at rest, it was stretched 0.25 and they stretched it a meter.
Oh, from there?
That's what it sounded like.
I don't know if it was from there. I think they just gave us this information so that we could find the spring constant. They say, it says something like, so mass is attached to a string that is stretched 25 centimeters by a force of 9 newtons. So I'm reading that as to stretch it 25 centimeters would require 9 newtons of force. At time t equals 0, the body is pulled 1 meter to the right. So I'm going to take x0, x naught to be 1. and set in motion with an initial velocity of 5 meters per second to the left. So this would be x prime of 0. They're giving us a velocity. That's the derivative. Rate of change of the position. This is linear motion back and forth. And that was 5. But it's moving to the left. So the velocity is negative. Okay? Right is positive direction, left. So x is decreasing at 5 meters per second. Okay. So we can use that to find C1 and C2. Cosine of 0 is just 1, so I get C1 plus C2, and sine of 0, when I put the 0 there, I just get 0. And that is 1. So that, right off the bat, allows us to solve for C1. And the derivative, let's find this real fast. X prime of t, cosine goes to negative sine, so I'm going to have negative omega naught's going to pop out because of the chain rule. So, however you want to put it, C1 omega naught sine omega naught t. And sine goes to cosine, omega naught's going to pop out, so we're going to have a plus C2 omega naught cosine omega naught t. Okay. And then we use our other initial condition, yeah? This goes to 0, I get C1 omega naught sine of 0, just gives me 0, so that all zeroes out. Plus C2 omega naught and cosine, that all goes to 0, cosine of 0 is 1. And we know that x prime of 0 is negative 5. So, that goes away. We get C2 equals negative 5 over omega naught. Okay. And what is, well, let's just leave it like that. So, our x of t, C1 is 1. So we just get cosine omega naught t plus C2, and that's 5 over omega naught, negative sine omega naught t, where omega naught is the square root of k over m. And we just solved for k. K was 36, m, the mass of it was 0.25 kilograms. Yeah, we could have done all this first, but whatever. 72, 144. 36 divided by 1/4.
We want to do 6 and 5.
What's that?
96 and 45.
144, and that's just 12, isn't it? Yeah, so omega naught's 12. 36 over 0.25. Okay, so we got, let's just put that in there, jeez. It's a nice number, I thought it was going to end up as a root. Okay, so some things you can tell about it. The period of the oscillation. Period is the time it would take to complete one full cycle back and forth. And what's going to be the period here? Two pi over omega naught. Yeah. Okay, so it's a nice multiple of pi. And the frequency?
Isn't it 2 different ones?
Oh, no. Those are the same. Yeah, so they, I mean, you know, if you graph cosine 12t versus sine 12t, they'd be off, but only by some sort of phase angle. It'd be a shift, because they both have the same period. So one would be a shift of the other. They are on the same cycle, on the same frequency. Same frequency, same period. So that's why you can write it as a single sine or cosine function. If you did the subtraction there, you get a periodic function with the same period. Frequency is just 1 over the period. Yeah, so it's just 6 over pi. And then here's the other thing that I will expect you to know how to do. We talked about last time, I brought my trig book, the amplitude. And it's just the square root of the sum of the squares of these amplitudes of the separate function. So it's going to be square root 1 squared plus, it doesn't matter, it could be negative 5/12, I'm squaring it. So we get square root of 1 plus 25 1/44. And if you get a common denominator, 144, you get 169 144. So they made this very nice. Because 169, isn't that that's also a square number. So it's 13/12. So you can find the amplitude. You can find all those things without crushing that in and writing as a single cosine function. That's good enough for me. Okay. All right. Any questions about the process? And this one is undamped, so we can just skip right to cut out the C. We can skip right to this part, do the characteristic equation, and find the general form of the solution. Okay. If it is damped in any way, then there's a different solution. We use the quadratic formula to derive it. Okay. Okay. So we're gonna mix it up today. Last time was pretty heavy duty, just straight ledger all the way through. We have a quiz. We're gonna start off with that today. Okay. So knock that out while you're still